This video is a review of the material that I covered in class on February 23rd, 2021, because unfortunately the prepare for class assignment did not show up because I made a mistake in assigning the permissions on the folder in Blackboard. In addition to that, there are a bunch of students in the class who are currently under quarantine, and it's only fair that they get some kind of a synopsis of what we did in class today. So if you were in class, this is a video that you can probably skip. But if you had questions, you might want to watch it. If you were not in class today, you definitely should watch this video. We started with a new definition, and it's not a hard definition. We're going to let G under star be a group. And let me make my handwriting a little bit better. And we're going to let H be a subset of G, and I'm going to insist that H is not equal to the empty set. And it turns out that if H under the same operation that G uses is a group itself, then we call H a subgroup of G. And we write H is a subgroup of G where we are reusing the less than or equal to symbol from other mathematics. It turns out that in abstract algebra, there's very little need for a less than operation, and that's why the symbol for less than gets reused for a subgroup. After looking at this definition, what we did is we did a bunch of examples. I am not going to try and remember all of the examples that we did, but we did a bunch of examples, and here are the kinds of examples that we were doing. And these are all based on the groups that you're already very familiar with. And what I want to say about this is that you should stop the tape and try and answer the question for yourself after each question that I pose. So this is going to be a long list of examples and what I'm also going to call non-examples. We're going to look at things that are and are not subgroups. And my first one is the set of rational numbers under addition a subgroup of the set of real numbers under addition? So stop the video and think about that for just a minute. The answer here is yes. Both things are groups. So both are groups. And Q is certainly a subset of R, and both of them have the same operation. So both use plus. Our second example is the set of integers, a subgroup of the set of real numbers. And here again, the operation in both sets is plus. And the answer here again is yes, and it's very much the same reason. Both are groups. Z is a subset of the reals, and both use plus for the operation. Well, let's see. What about the next example? Is Z, well, let's make it Z. Let's look at N. Is N under its plus a subgroup of the real numbers under addition? And if you think about this one, the answer is no. And the reason why is this. N under plus is not a group. And it's not a group because 0 is not inside the natural numbers, so we have no additive identity inside of the natural numbers. Okay, let's look at another example. Let's look at Q star under times. Is that a subgroup of R star under times? And the answer to this question is yes. And I want to remind you that Q star is just Q, take away 0, and R star is R, take away 0. And both of these things are both of these are groups under multiplication. So both Q star under multiplication and R star under multiplication are groups. And clearly Q star is a subset of R star. So all of this together says that Q star under its multiplication is a subgroup of R star under its multiplication. Let's see, I guess let's move on to the next panel because I don't want to get crammed. Let's look at this example. Is Q star under times a subgroup of R under plus? And I want you to stop the video and think about this question, and after you make a guess on the answer, then start the video back up. Okay, well, the answer to this is no. And here's why. Yes, both of these things are groups. So they are both groups. And yes, Q star is a subset of R, but the group operation is different. Q star is a group using times for the operation, and R is a group using plus as the operation. And since they have different operations, that means that Q star under its multiplication is not a subgroup of R under plus. So that's why it's important to realize that the definition of subgroup requires the group operation to be the same. Let's do one more example to kind of get the flavor of this sort of stuff. Actually, I've got a couple more of examples to do. So, and not if, let's say is. Is. Let's do Q plus under times a subgroup of R plus, well, R star rather, under times. Now in this one, again, I want you to stop the video and make a guess before going on. And hopefully you've done that. Q plus is the set of all x's inside the rational numbers such that x is strictly bigger than 0. And it turns out that Q plus under times is a group. And very briefly, if you look at the product of two, if I look at two positive rational numbers, the product will be positive and the product will be rational. So that means the product will be inside Q plus. Associativity is multiplication is always associative, so I'm not even going to write that down. 1 is clearly inside Q plus. So I have a multiplicative identity, and if A is inside Q plus, then the reciprocal of A is also positive, so it will also be inside Q plus. And so all of this means that Q plus under times is a group. And Q plus is clearly a subgroup of R star, because R star is all of the real numbers, take away 0. And so, yes, Q plus under times is indeed going to be a subgroup of R star under times. Let's wind up this one with one last example. This is coming from matrix stuff. I want you to recall that GL2 is the set of 2 by 2 matrices where the determinant is not equal to 0, and M22 is simply the set of all 2 by 2 matrices. And this is technically where A, B, C, and D are all real numbers. And under this notation, we're going to be assuming that GL2 is also over all real numbers, and GL2 is clearly a subset of M22. So is GL2 let me get the operations here. Is GL2 under times a subgroup of M22 under plus? And the answer to this one is going to be no. And the reason why is we have different operations. It is true that both of these things are groups, but they have different operations. So that means this is that GL2 is not a subgroup of M22. If I think about whether or not GL2 under its times is a subgroup of M22 under its multiplication, the answer to this is also no, and the reason why here is that while we're using the same operation in both of these algebraic structures, M22 under times is not a group. And it's not a group because any matrix that happens to have determinant equal to 0 has no multiplicative inverse. So if the determinant of A is not equal to 0, then A inverse does not exist. So we don't have the fourth group axiom satisfied in M22 under times. Finally, with these matrix groups, I can ask the question, is GL2 under plus a subgroup of M22 under plus? And the answer to this one is also going to be no, and it's because GL2 under plus is not a group. And this is not a group because the 0 matrix, which is the additive identity for matrix addition, is not inside GL2, since the determinant of the 0 matrix is a big fat 0. And then we have one last example that I want to do that we did in class that is also worth going over. And that is going to be this. Is Z5 under its plus a subgroup of Z under its plus? Stop the video and answer this question, and when you think you have this question answered, start the video back up and see whether or not you've gotten the answer right. We spent quite a bit of time talking about this one in class, and so I want to kind of remind people of what that was, and for those of you who were not able to be in class today, put in a full explanation of this, because this is an important example. Z5, remember, is the equivalence classes mod 5. So it basically can be thought of as 0, 1, 2, 3, and 4. And the addition stands for addition mod 5. And Z5 under its addition is a group. You have previously proven that in class. So this guy is a group. And let me clean that notation up as well. Z is, of course, all of the integers. So it's 0, plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 4, plus and minus 5. And so on. And superficially, it certainly looks like Z5 is a subset of Z because we're simply restricting it down to five particular numbers. But it's important to understand that addition mod 5 is not the same as ordinary addition. And the addition for Z is ordinary addition. And so what I want to be thinking of is a specific kind of example being built on these two things. Inside Z5, under its plus, if I look at 4 plus 4, well, that is equal to 8, but 8 is equal to 3 mod 5. And so I have to be thinking about 4 plus 4 is equal to 3 in Z5. So 4 plus 4 equals 3 in Z5 because I'm reducing everything down mod 5. Inside Z, however, 4 plus 4 is just equal to 8. I'm not doing any reduction mod 5. And so there's a big difference between the two operations. You can think of it as the answer is not the same in the two groups, but it's just as important to realize that this operation and this operation, even though we're using the same symbol to denote them, these are different operations. And because they're different operations, the answer to this question is no, Z5 is not a subgroup of Z. That ends the first part of the stuff that we were going over today. And I'm going to go ahead and quit this video because it is already pushing 20 minutes.